Okay, today now we are going to see the special purpose registers inside the 8086 processor. So in 8086 processor, there are different types of special purpose registers. Those are ES means extra segment register, CS means code segment register, and SS means stack segment register, DS means data segment register, and IP means instruction pointer. So these are the registers available in the bus interface unit, and there are some other special purpose registers also available in the execution unit. Those are stack pointer, base pointer, source index, and destination index. So before going to discuss the use of these special purpose registers, let me discuss another point to understand these special purpose registers in detail. You can see this diagram. So this is the memory interfacing diagram with 8086. So this is your 8086 processor, and this is the decoder, and this one is the memory unit. Okay. Now see, these are the address lines. So for 8086 microprocessor, there are address lines are 20. It is having 20 address lines. So 8086 processor is having 20 address lines. Those are labeled as A0, A1, A2, and so on, A19. So these address lines are connected through the decoder into the memory. So as all of you know, the decoder output, decoder truth table. Suppose if you take a decoder truth table inputs A, B, what are the outputs? B0, B1, B2, and D. Okay. If A, B are 0, 0, D0 will be 1, and then all other will be 0. If it is 0, 1, this will be 0, this is 1, like this. If it is 1, 0, this is 0, 0, 1, 0. If it is 1, 1. That means what? For the decoder, for a given input, only one output will be high and remaining all other output will be 0. So that is the reason. Suppose if there is a address is generated from the A0 to A19 lines, then at a time decoder output will be only one output will be 1 and remaining all other outputs will be 0. Such that what happened? Whatever the line is having 1, that corresponding memory location will be activated and it can be used by the 8086 processor. So the main point is here, the memory unit will be activated only, the CPU will be activated only one memory location at a time. That is the point. So after activating, then it can perform either writing operation or reading operation onto the memory. Okay, in detail operation we will discuss later. So here our point is, we are having different kinds of segment registers in the 8086 processor. What are those? Those are one segment register, code segment register, data segment register, and stack segment register, and extra segment registers. Similarly, we are having another extra segment, another special purpose registers, that is stack pointer, base pointer, and instruction pointer, and source index and destination index. So these registers: core segment, code segment register, data segment registers, stack segment registers, extra segment registers. These registers are called special purpose register, and which will hold the base address of the segment. Base address. What it will hold? Code segment registers, data segment register, stack segment register, and extra segment register will hold the base address of the memory location. Similarly, stack pointer register, base pointer register, instruction pointer, source index, destination index will hold the offset address of the memory. Offset address of the memory. So you may ask the question, why the two addresses? Why the two different addresses? See here, memory location can be accessed by the address of this particular memory location. And this address first will be stored into the CPU. So as you are aware, the 8086 is having 20 address lines, so that it can able to access 2 power 20 memory locations, isn't it? So this is the 0th memory location, this is the 1 memory location, and so on it goes on, and the last memory location is 2 power 20. So that means here the CPU address will be the 20 bit. CPU address will be the 20 bit. That means what? Here the first address is 20 zeros. That means the first address is 20 zeros, 0, 0, 0, 0, 0, and 0, 0, 0, 0. Like this, it will be repeated up to 20. So it is very inconvenient to represent the 20 zeros. So that is the reason 20, we will represent the number in the form of hexadecimal. So 20 zeros will be now become 4, 5 zeros. 20 zeros will become now 5 zeros in the hexadecimal. So like that, it will be, next address will be 19 zeros 1. The next address will be 18 zeros 1 0. Then next address is 18 zeros 1 1. Like that it will keeps go on. So now you catch the point. The memory address is 20 bits. But in the 8086 processor, all the registers are 16-bit size only. Okay, code segment register, and a data segment register, and a stack segment register, and an extra segment register. So all these registers can hold only 16-bit address. 16-bit address. Similarly, the stack pointer register is also 16-bit register. That's why 8086 is called 16-bit processor. Okay. But see, in order to access this memory location, the CPU has to generate the 20-bit address. CPU has to generate the 20-bit address. But here these register will hold only 16-bit. So how it is possible to generate a 20-bit address by using 16-bit registers? That is the question. Here one more point we have to discuss, that is why we are having 4 segment registers. 4 segment, data segment, stack segment and extra segment. Because here memory will be classified into 4 different categories. Our memory will be categorized into 4 parts. This is code segment memory code segment part, and a data segment part, and a stack segment part, and an extra segment part. So this memory will be split into 4 different categories: code segment, data segment, stack segment, and extra segment. That is the reason, in order to access the code segment memory, the CPU will read the address from the code segment register. If the CPU try to access the stack segment memory location, then the CPU will read the data from the stack segment register. Okay. Like that, if the CPU is accessing any one of these 4 memory locations, then the CPU will first read the address from the corresponding register, then it will generate the address. From there it can access the memory location. Since the memory is partitioning to 4 different categories, that's why we are having 4 segment registers to provide the base address. Base address means the starting address of the segment. So say it is this one is the starting address. So the starting address will be stored into the corresponding segment register. So data segment register starting address will be stored into the data segment register. Stack segment memory starting address will be stored into the stack segment register in the CPU. So why the address is partitioned into 2 parts? That what are the 2 parts? Of base address and the offset address. As you know that the CPU has to generate 20-bit address. 20-bit address. Why? Because the address for memory location is 20 bits. But unfortunately 8086 is having only 16-bit register. So the question comes, how can the CPU generate 20-bit address by using the 16-bit register? So it is only possible to generate 20-bit address by using 2 16-bit registers. 2 16-bit registers. That's why the address will be divided into 2 parts. One is base address plus offset address. Offset address. Okay. So this will be 16-bit and this will be 16-bit. Okay, so the base address will be stored into the base registers and the offset address will be stored into the stack pointer, base pointer, instruction pointer, or source index or destination index. So which will be used, offset address will be used, and which base address will be used, that is decided by the programmer. Okay, there are some default segment base register and offset registers are provided for different accesses. Okay, for example, if you are accessing code segment location, if the CPU wanted to access the code segment memory, okay, then where it will take the base address? So the base address will be taken from the code segment register and offset address will be taken from the instruction pointer by default. Okay. Suppose if the CPU is accessing stack segment memory locations, then the base address will be taken from the stack segment register and offset address will be taken from the stack pointer or base pointer. Okay. Similarly, if it is accessing the extra segment register, if the CPU accessing extra segment register, the base address will be taken from the extra segment register and the offset address will be taken from the destination index. These are the default address generations by the CPU. So if the CPU is accessing data segment register, data segment memory location, then the CPU will take the base address from the data segment register and offset address can be taken from the source index register or stack pointer or base pointer. So it can be source. It can be BX register. Offset address can be taken from the BX register or any other general purpose register, or it can also taken from the destination index also, or it can be direct 8-bit address, or it can be 16-bit address. So in future we will in detail discuss about how the offset address will be generated, how the base address will be generated. We will deeply discuss in future classes. So but just time being, you just remember the purpose of these segment registers inside the CPU. What it will hold? It will hold the code segment register will hold the base address of the code segment memory location, 16-bit base address. Similarly, data segment register will hold the base address of the data segment memory location. Likewise. Okay. So, but here one point, see, in order to generate the 20-bit physical address, that will be split into two parts. One is base address and offset address, offset address. So if you directly add this base address plus offset address, then will you get 20-bit? No. So if you directly add this 16-bit to 16-bit, you will get only 16-bit. Then how the CPU can generate 20-bit address by using two 16-bit registers? That generation of 20-bit address by the CPU is called physical address. Physical address is called physical address. So how can we generate physical address? We will discuss in the next class.